After decades of research, construction, and a Christmas Day launch, we are getting more full-color images from the James Webb Space Telescope.
When the James Webb Space Telescope turned its golden flower-like eye toward the depths of the cosmos, scientists expected to see galaxies as they existed in the early universe, small, turbulent, and slowly evolving into the grand spirals and ellipticals we see nearby today. Instead, what it revealed defied expectations and shook the foundations of our understanding of cosmic history. In its early deep field surveys, Webb uncovered a universe far more complex, developed, and structured than anyone had predicted for such a young epoch. Galaxies that should not have existed for billions of years, because theory said there hadn't been enough time, were there, shining with shocking maturity. Before we start, smash the like and subscribe buttons for more updates. These distant galaxies, seen as they were just a few 100 million years after the Big Bang, showed signs of being massive, dusty, and well-organized. Some had rotational structure, some bore heavy elements, some were red and quiescent, seemingly already finished with the most furious bursts of star formation. This revelation forced astrophysicists to confront a glaring discrepancy between theoretical models and observed reality. The universe, it seems, built itself faster and more aggressively than expected. In short, the early cosmos was not a gentle nursery but a chaotic forge. Webb's highly sensitive infrared instruments allowed it to peer through veils of cosmic dust that obscured previous observations. Unlike Hubble, which was limited to mostly visible and ultraviolet light, Webb could see the red-shifted glow of ancient stars whose light had traveled for over 13 billion years. And what it saw was startling. Galaxies that rival the Milky Way in mass, already taking form within 300 to 500 million years of the Big Bang. Their brightness, their structure, their sheer presence in the primordial void posed urgent questions. How did so much mass coalesce so quickly? Where did the raw material for such rapid star formation come from? The standard cosmological model, known as lambda cold dark matter LCDM, predicts that the formation of such massive galaxies takes time, lots of it. The early universe, following this model, should have been dominated by small, irregular proto-galaxies clumping together slowly, gradually growing into the giants we see nearby today. Yet the James Webb Space Telescope revealed not only massive galaxies, but also signs of mature stellar populations, chemical enrichment, and complex morphologies. These galaxies weren't merely assembling, they were already assembled. In many cases, they appeared to have evolved stars and environments incompatible with such an early cosmic era. This contradiction is not just academic. It touches the very heart of how scientists model the life cycle of the universe. The formation of galaxies is governed by the interplay of dark matter, gravity, gas dynamics, and feedback from stars and black holes. If galaxies are forming earlier and growing faster, then something about one or more of these components must be misunderstood. It raises the possibility that dark matter behaves differently than expected, or that gas cooled and collapsed into stars more efficiently under certain unknown conditions. Alternatively, there could be entirely new mechanisms at play in the early universe that haven't yet been discovered or understood. One particularly intriguing implication concerns the growth of black holes. The detection of extremely luminous quasars, galaxies with actively feeding supermassive black holes, so soon after the Big Bang had already strained theoretical models. But Webb's data deepened the puzzle. If galaxies were already massive and well-formed, the black holes at their centers might have grown in tandem, or even preceded their host galaxies in mass assembly. This flips the standard narrative of galactic evolution on its head. In some of the galaxies Webb observed, the energy output from their central black holes suggested enormous masses that defied known models of black hole seed formation and growth. Could black holes form directly from collapsing clouds of primordial gas, bypassing the stellar phase entirely? Webb's observations lend credence to such radical possibilities. Another layer of surprise came from the types of stars observed, or rather inferred from the light spectra. Some early galaxies showed signs of having population 3 stars, the theoretical first generation of stars composed only of hydrogen and helium. These stars were thought to be massive, short-lived, and extremely rare in observational data. Webb may have finally given humanity a glimpse of their remnants or of the environments they shaped. Yet alongside such ancient, pristine systems, Webb also revealed galaxies that were already chemically enriched with elements like oxygen, carbon, and even iron, metals that should have taken multiple generations of stars to forge. The juxtaposition of ancient simplicity and unexpected complexity suggests that the timeline of star formation may need drastic revision. It is possible that the first stars formed far earlier than once believed, perhaps within a mere 100 million years after the Big Bang. If true, that would shift the entire understanding of when and how the cosmic dark ages ended, when the first light began rionizing the neutral hydrogen fog that filled the universe. Webb has pushed the boundary of that transition further back in time, showing galaxies with active star formation and ionizing radiation operating earlier than any models had prepared us to see. Even more provocatively, some of the galaxies spotted by Webb appeared to be in groups, even clusters, suggesting that large-scale structure, once thought to emerge over billions of years, was already taking shape. The cosmic web, a vast lattice of filaments and voids made of dark matter and gas, may have been forming earlier and more efficiently than expected. If confirmed, this challenges assumptions about the behavior of dark matter in the early universe and the rate at which gravity assembles mass on grand scales. It could also imply that the seeds of superclusters, the largest structures in the cosmos, were planted shockingly early. These findings ripple outward into other domains of cosmology. For instance, the early emergence of complex galaxies complicates efforts to use galaxy counts as a measure of cosmic expansion. Redshift alone no longer tells the full story if galaxies can mature at different rates or exhibit unexpected brightness. This complicates efforts to constrain parameters like the Hubble constant or the nature of dark energy. In other words, Webb is not merely showing pretty pictures of distant galaxies, it is challenging the very toolkit cosmologists use to decode the universe's secrets. What's more, the observational confidence in Webb's data has made it hard to dismiss these anomalies as flukes or data artifacts. Webb's instrumentation was built to the most exacting standards, cooled to cryogenic temperatures to minimize interference, and calibrated with years of careful testing. Its findings have been cross-checked with multiple observing strategies and analyzed using independent methods. The sheer number and consistency of early massive galaxies now being reported make it clear this is not a statistical outlier, but a genuine cosmic phenomenon. The implications also reach into the realm of theoretical physics. If the standard model of cosmology cannot fully account for these observations, there may be a need to revisit its foundational assumptions. Could inflation have seeded structures more aggressively than currently believed? Might there be a role for exotic particles or fields that influence the early distribution of matter? Some researchers have speculated that what Webb is revealing could point to deviations from Einstein's general relativity at cosmic scales, or to interactions between dark matter and ordinary matter that accelerate structure formation. Such speculation, while exciting, must be tempered with the understanding that Webb has only just begun its mission. These early findings represent only the tip of the observational iceberg. As more time is allocated to survey the distant universe, more galaxies will be found and patterns may begin to emerge that help refine or reinterpret these early surprises. Still, the paradigm shift has already started. The expectation that the early universe was a slow, simple place of gradual buildup has been decisively overturned. In its place is a dynamic, bustling cosmos, one that got a far faster start than anyone had dared to imagine. Beyond the scientific ramifications, the emotional and philosophical weight of these discoveries cannot be overlooked. For decades, the story of the universe has been one of humble beginnings and slow progression toward complexity. Webb, however, paints a different picture, one in which the universe was ambitious from the outset. It didn't take eons to sculpt beauty and complexity from chaos. It leapt into it almost immediately. This realization reshapes humanity's place in the cosmos, not because it moves us spatially or temporally, but because it reframes the nature of cosmic evolution itself. Webb's observations also underscore the value of relentless curiosity and the tools we build to pursue it. The telescope took decades of planning, international cooperation, and technological innovation to create. It is the most ambitious observatory ever launched, orbiting the Sun 1 million miles from Earth, shielded from the heat of the solar system and focused solely on the faint glow of the ancient universe. That such a machine can rewrite the textbook of cosmic history within months of operation is a testament to the precision of human ingenuity when driven by wonder. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what JWST will reveal about distant galaxies next? We want to hear from you. Thank you for watching and see you next time.